configuration which you'll be able to see more clearly in a couple of minutes. 7 in series by 3 in parallel, which, as you can see, the total capacitance comes to just under 4,300 microfarads, with a bias of ability of over 3 kilovolts. There are charge regulating resistors across each capacitor terminal, which are 10 megaohm half watt wire wound power resistors, which serve as voltage dividers, so to ensure that each sub-bank, if you will, the capacitor bank is equally charged, so that no branches are overcharged given the total capacitor bank charge. There's also a normally closed relay attached to a graphite load, which is always, as I said, normally closed, so the capacitor bank is always shorted when the device is off and can only be charged effectively when it is turned on. So the charging system consists of a 3 kilovolt AC transformer. Its max current output is 60 milliamps, and we have a bridge rectifier to keep the capacitor to keep positive bias because these capacitors can't be reverse charged. The bridge rectifier is more than capable of handling this because it's rated over 2 amps. And there's a further high voltage diode with a 10 kilovolt reverse working voltage in order to protect the transformers and to prevent any backwards current from the capacitor bank. So here's the illustration. As you can see, there's the transformer through the load resistor to limit the current, which goes into the bridge rectifier. It's a 10 kilovolt diode to protect it. And the capacitor bank there, you can see, that's what I mean by 7 in series by 3 in parallel across there. And each resistor across the 10 megaohm resistor is regulating the charge by the voltage divider. There's a normally closed discharge switch with the graphite. And the arming switch, to clarify, arming means to transfer charge from the capacitor bank to the rails. We have in that box we have 2 very large high current high voltage relays, one of which handles the transfer of charge from the capacitor bank to the rails. The other one handles, the other one is the normally closed one, which is always shorted unless the device is turned on. So now I'll hand you off to Dani, who will describe the gas injection system.
Alright, so the next major module to the design of the railgun is the gas injection system. And this system is critical to the functionality of the device because if the projectile were fired from rest, the ohmic and frictional heating would likely weld it to the rails. And so by giving it an initial velocity down a non-conducting path before it reaches the conducting portion of the enclosure, this greatly reduces the amount of time that the projectile spends in contact with the rails, and consequently the amount of heat is greatly reduced, so this problem is avoided. And it also reduces the amount of rail erosion, which facilitates multiple firings, which is one of the main goals in railgun construction, is to be able to fire it multiple times before it breaks down. And so it was decided that we needed an initial boost of at least 50 meters per second in order to avoid these heating effects. And so the graph on here shows that we can easily overcome this within a 500 pound per square inch input pressure range. And so this kind of became the basis for part selection for this part of the railgun. And ultimately, we decided on kind of a paintball style injection system because the parts are easy to find, they're compact, they're relatively inexpensive, and we can easily integrate them into our system. And so the main components of the gas injection system are shown on this block diagram here. And so first you'll see kind of on this side is a 20-ounce CO2 tank, which gives an output pressure of 800 psi. And then that attaches to it's a typical paintball style regulator. And this allows us to adjust the pressure between 0 and 500 psi and to monitor it so that we know we're getting the same pressure each firing. Because we want to have the same injection velocity each time because we do a certain pulse width as determined by the pulse shaping inductor. So we want to spend the same amount of time in contact with the rails each firing. And so the next component is not actually a paintball component, it's a heavy-duty solenoid valve, and this was chosen for robustness and safety. And so what actually happens when the fire button is pressed is that the microcontroller sends out a 200 millisecond signal. And using a relay, this low power signal is able to switch the higher power 120 volt AC signal that the solenoid valve requires for operation. So once the coil inside the valve is energized, a magnetic field is created, which pulls up the ferromagnet, which seals the valve and allows a short burst of gas to go through. And finally, you'll see that this valve is connected to the rail enclosure using a gasket. And so one of the great features of the gas injection system is that it stands alone. It doesn't draw any power from any other part of the railgun. And this is why we'll be able to give a demonstration later of a simulation of a railgun firing using just the gas injection with a small foam projectile and the user interface that Kevin showed you earlier. And another feature of the railgun is that the projectile itself is made from a conducting material. So after it's given the boost and it contacts the rails, which are energized, it completes the circuit and triggers the discharge of the capacitors. So the timing of switching between the injection system and the actual energizing of the rails is not necessary. And with that, I will pass you on to Andrew.
So, as Danny said before, railguns are notoriously self-destructive. So while you have, because your projectile is going so quickly out, you're going to have both erosion along with all the current going through, and while the projectile is going this way, everything else wants to push this way because of the mass force. So there are two primary parts when you actually look at the accelerator rails, which would be you look at in the middle, the copper, which is the conducting path. And there's also a non-conducting path in the like G9, which is a very sturdy material. So our main concern with constructing this was having rails that were extremely conductive along with an enclosure, which would be the green outside part, which you can see here, which is screwed in by 46 stainless steel screw. And these are all extremely sturdy and robust to make sure that everything maintains form, nothing blows out to the side. So while we have this, and you can actually see the cutaway, the copper would be the little L-shaped looking bars, and these are actually contacts that come up here that connect to the power supply and everything. So Garrett G11 is rated to handle up to 58,000, 59,000 passes per inch of tensile force, and the screws are rated to handle about 80,000. So everything here is going to be trying to keep this form as sturdy as possible. And inside is the rail spacers, which extend up to here, and then the gas injection connects here to the aluminum base plate, fires it through here and accelerates it all the way through till it contacts here, where this is where the electromagnetic acceleration takes over.
All right, so I mean, now that the basics and the details of our project have been explained, people ask me if there's any technical or non-technical questions. Did we know, actually, like you said, this is a museum piece pending further testing because of safety concerns here at the by a number of people. It was unable to be tested on. So the furthest we've gotten as far as testing goes is the gas injection system. That works well, but we unfortunately want to test those. So pending further testing, this machine will give us a day and we'll be able to work.
How far can we shoot?
How far? So just from the numbers that we crunched, we were expecting muzzle velocities between 500 and 700 meters per second.
I have a couple of questions.